what I've decided to do is try to work as many of these Lewis structure worksheet problems as I possibly can for you guys, since I'm not going to have enough time to cover them in class, so you can actually have them at home to work on. So I'm going to kind of move through these relatively quickly. Hopefully you can kind of keep up, and if you have any questions, the only thing I can do is either tell you to call me, it's not call me, but come in or email me or do whatever it takes to try to get these understood. Alright, so let's just jump in and go right for it. The first thing you always want to do, and again, I would recommend getting out the steps that I've given you as I go along. That way you can kind of keep up with the steps, because I may skip over some of them, but that way at least you can see what I'm doing. And on the sheet I gave you, I actually had this one labeled CF4, that way you know what it is. So carbon tetrafluoride. So what I want to do is I want to list each element and how many there are. Well, I know there's one carbon, I know there are 4 fluorines. And then I want to determine how many valence electrons each element has. Well, I know that carbon is in group 14, so it's got 4. Fluorine's in group 17, so it's got 7. And then just do the math here. So 4, 28, for a total of 32. Alright, I want to decide what my central atom is. Well, carbon is present, and I know carbon is always going to be the central atom. And then I want to connect all 4. Now, this is where you're really going to have to pay attention. I'm going to go ahead and draw the structure as it is supposed to be drawn. I'm not going to do the skeleton structure and then change it and fix it and move it and bend it the way it's supposed to be bent. I'm just going to go ahead and draw it the correct way that you're supposed to draw it. So I want you to see how hopefully you'll get to the point where you don't even have to do the skeleton. You could just go ahead and draw it the correct way. Alright. So my next step is to connect all the outer electrons and then count the bonds and subtract that from the total. So I have 4 bonds, so that's 2, 4, 6, 8 total, which will give me 24 electrons left. Alright. My next step is to fill up all the outer electrons with the valence electrons, except hydrogen. Hydrogen is not present here, so that's good. So I can go ahead and start labeling 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Well, good news is I'm completely out of electrons, and so my structure is complete, as long as everybody has its full octet. And if you want to count them, you can count them, but I can go ahead and tell you that every element has its full octet. Alright, so that is the structure that you're going to have to draw. So now let me go ahead and do a few other things. The first thing I'm going to do is I'm going to list the model, what model this fits. Then I'm going to list the shape, and I'm going to do this for every single one of them, but I'm not going to label it every time like this. I'm just going to go ahead and write all the answers down. The angle, the hybridization, and if there's a lag in this video, I still have yet to figure out the best way to have the settings so there is no lag in the video. Now, and I'm going to go ahead and tell you this. On the test, you're going to have to tell me these 5 things. The model is not a part of the test. That is just to help you figure out the shape and the rest of it. Because if you have memorized that sheet that I gave you, once you know the model, you should know the rest of these things. So that's what I'm trying to help you out with, is if you memorize the model, then you can figure out the other 5 of these that are a part of this. Alright. So, what is this model? Well, remember, it's the A, B, X, and EY model. And again, we may not have this E. That's only for a certain case. And so what does A stand for? A stands for the central atom. B stands for the atoms that are bonded to the central one. And then E is those extra pairs of electrons only on the central atom. So one more time, B is the atoms bonded to the central atom, and E is the extra pair of electrons on the central atom. Alright, so I could just look at this and tell that there's not any E, so I don't need that. But there are 4 bonded atoms. So the model is AB4, and that shape that corresponds to that model is tetrahedral. The angle of a tetrahedral is 109.5. The hybridization. Let me just go through and kind of help you out with this one. Remember, there's 1 S, there are 3 P's, there are 5 D's, but the biggest structure you'll ever use will only have 2 of them. And so that's going to be S, and then P1, P2, P3. And it doesn't matter where you start or how you go, but no matter what you do, this is going to be an SP3 3 hybridization, polarity. If all of those F's had a rope tied to that carbon, none of them would win, right? Because all the F's are the same strength. And remember, this is a 3D molecule. That's the reason I've drawn this way. You've seen me do this enough now to know that's the reason I've drawn it like this. So the polarity is nonpolar. And then hopefully I've covered this in class by now. So the IMF this would exhibit is a London dispersion force, or an LDF, because the only type of IMF that two non-polar molecules can have is an LDF. That's it. There's no other IMF that two non-polar molecules can have. All right, so hopefully you got the first one. I'm going to move on to the second one. All right, so let's look at BF3. All right, so boron trifluoride is the name of this. Boron has 1, fluorine has 3. Boron is in group 3, so it needs 13. Excuse me, it's in group 13, so it needs 3. Fluorine is in group 17, so it needs 7. So 3, 21, 24. Now, I'm going to go ahead and make this little note because you're probably not going to remember this, but you really, really, really need to remember this because boron is one of your exceptions. So you need to know all the there's only 3 exceptions. Hydrogen and helium, of course, they will never have an octet. And I want you to think about the reason that is. I'm going to say it in a minute, but I want you to think about why hydrogen and helium will never have an octet. All right. So boron only needs blank electrons. Now, specifically that I'm talking about a valence. It does not need 8. It does not need a full octet. So this is your exception to this rule, because when you draw it, it's not going to make any sense, and you're going to try to figure out what's wrong. But boron, remember, only needs 6. All right, so once it's got its 6, it's perfectly happy, it's perfectly stable. All right, so boron is going to go in the center, and remember, I've told you that I'm only going to draw this the way that I already know how to draw it, and if you need practice of doing it the other way, then that's fine, but I'm going to go ahead and draw it how I know to draw it. All right, I went ahead and connected all the outer ones. So now I'm going to subtract the bonds. So 2, 4, 6. So 24 minus 6 gives me 18. Then I'm going to fill up the outsides. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, and see, and this is proof that boron only needs 6 electrons. Okay, remember, you have to remember that boron only needs 6 electrons. Otherwise, you're not going to be able to figure this one out. All right, so let's talk about the model. There are 3 things bonded to that central atom, so it's AB3. There are no E's there. So that model fits this shape. And I want to see if you say it in your head before I finish writing it. Okay, trigonal planar. The bond angle is 120 degrees. The hybridization is sp2, and again, it's sp1, p2. The polarity is non-polar, and again, if I gave all those F's a rope to try to pull on the boron, none of them win. And the only type of IMF that 2 non-polar molecules can have is an LDF. All right, so hopefully that takes care of that. Let's move on to the next one. Now, I know that what you're going to think here is that NF3, that's going to look exactly like BF3. No, it's not. And you're going to see why it's not. And remember, boron only needs 6 valence electrons. Nitrogen needs 8. And so we've got to account for that shape difference here, okay? All right, so let's go ahead and figure out our valence electrons. So there's 1 N. There are 3 F's. Nitrogen is in group 15, so it needs 5. Fluorine's needs, so it needs 7. So 5, 21, that is 26 total. All right, again, I'm telling you now, I'm drawing these as I know how to draw them. And I left it like this for a particular reason, and you're going to see why in just a minute. All right, so let me go ahead and count my bond lines. 2, 4, 6. So 20 minus 6, that gives me, excuse me, 26 minus 6 gives me 20. Now I'm going to fill up my outer valence. 2, 4, 6, 8, 10, 12, 14, 16, 18. And now hopefully you can kind of see why I left that top open. I have 2 left. What is the rule for any valence electrons that are left once all your outer atoms have their octet? They must go on the central atom. And that is exactly why I drew this like this. So what does this mean? Those two electrons are the lone pair. And you've got to remember that this is a three-dimensional structure. I can't make this 3D on this flat board. So you're going to have to recognize the fact that those lone pair of electrons act and take up just as much space as that line does, even though you can't tell. Okay, so you have to account for the space that it's going to take up, and that's where it's going to take that space up. All right, so let's talk about the model. Okay, so hopefully you can recognize the model. And again, the A is the central. How many atoms are bonded to this thing? Hopefully you said B3. And remember, what else do we have here we've got to account for? We've got that E that's the lone pair that's around that central atom. So it's AB3. So here's what I would like for you to do. Pause your video, see if you can fill out the rest of the things. The shape, the bond angle, the hybridization, the polarity, and the IMF of this. See if you can do that without my help. Because the more you can do by yourself, the better off you're going to be. Alright, so the shape for this trigonal, pyramidal, or pyramidal. I think I misspelled that, but you get the point. It's pyramidal. Alright, the bond angle is 107 degrees. The hybridization is S, P1, P2, P3. It is sp3. And remember, if it ever has an E in its model, it's automatically going to be polar. Alright, and so the IMFs, remember there are two options for polar molecules for IMF. There's either dipole-dipole or hydrogen bonding. And you know one of them should obviously be out. Hydrogen bonding must have a hydrogen and fluorine, oxygen, or nitrogen. Must have FON. Now, the fluorine is present, however, the most obvious thing is not there. So hydrogen bonding is automatically knocked out, which only leaves you dipole-dipole. Alright, so hopefully that is relatively simple enough for you. Okay, I'm going to go ahead and be honest with you guys. 4 and 5, I'm not going to test you on. I can do it later, and I may come back and do another little session, or I can do it in class. However, I don't want to take the time up to do it in class because, I'll tell you what, I'll go ahead and draw 4, and if you want to see if you can figure out how this structure was achieved, that would be a really good idea. And I'll go ahead and tell you the model is the AB3 and see if you can figure out all the information about it. That is how that structure is drawn. So again, see if you can figure that information out. And 5, I'm not even going to go anywhere near. Alright? But I do want to do one that is very special, that you're going to have to do one like this on the test. And it is right here. The nitrate ion. Because I'm telling you now, you're going to have to do a polyatomic on the test. So NO3 negative. So let's talk about how this is special. And it's in your notes, and I made a point about it whenever we were covering them. However, I don't know if any of you paid attention to it when I was talking about it. Well, it starts off just as normal, alright? So we have nitrogen, we have oxygen, we have 1, we have 3, nitrogen's at 15, so it's got 5. Alright, so that is 6, no, excuse me, not 6, where did that come from? So that is 5 and 18 for a total of 23. Right off the bat, an alarm should be sounding in your head. And I really do hope it is. I hope an alarm is going off because something is wrong. What is wrong with this number? What is wrong with number 23? If you're saying that it is odd, you are correct. Remember, there's no possible way an electron will ever be by itself. Well, since this number is odd, that leaves an electron to be by itself, which is impossible. So, did you do the math wrong? No, you didn't do your math wrong. There's something you have to account for when ions are present, and it's right here. You have to account for that charge. So what is that charge telling me? That charge is telling me that I have gained 1 electron. Now, how do I know that I have gained an electron? Now, specifically 1 because it's -1 charged. I have gained 1 electron. The way I know I've gained is because it's negative. Hypothetically, let me just throw this out here at you just so you're on the same page with me. What if this polyatomic we were trying to draw was NH4 positive? What would the positive tell me? The positive would tell me that I have lost 1 electron. Alright, so that's the difference. Now, how do we account for that? Well, this is the way we account for it. We have to add 1 more electron. Okay? What would we do for the NH4 one? We would have to subtract an electron. What if the charge was like carbonate and it was CO3 2 negative? Well, we'd have to add 2 electrons. Okay? So again, that's how we account for it. So now you have an even number. You're good and ready to go. Alright, so now I know that this is going to be drawn like this, and again, I'm just drawing it as I know how to draw it. So let me account for the bond lines. 2, 4, 6, so 24 minus 6 leaves me 18. My next rule is fill up my outer valence. 2, 4, 6, 8, 10, 12, 14, 16, 18. Alright, well, I'm done. So that's it. Let me go ahead and tell you now. Does nitrogen have its full octet? The answer here is no, it does not. So here's what we got to do. We got to figure out how to get nitrate. Its valence electrons, and I've said this in class before, and I hope you remember it. Because here's what's going to happen. If you move any of them, and I'm just going to take these 2 right here, the ones that I had drawn right here, I'm just going to take them and I'm going to move them to nitrogen. All right, now, let's look. Nitrogen has its 8, right? So it's got 2, 4, 6, 8. We'll look at oxygen. It only has 2, 4, 6. So here's my phrase. And no matter what oxygen you do it with, this is going to happen. If you can't move them, then share them. If you can't move them, then share them. And what in the world do I mean by this? What I literally meant is those 2 electrons that I moved, that I took from right here, I can't move them because that takes away a valence electron. So what I'm going to have to do is I'm going to have to share them. And when you share them, what does that create between these 2 atoms? What that creates is a double bond. Alright, now, so this is going to look like this, and this is going to occur. And I know what you're doing. I know exactly what you're saying. Why did you pick that one? Why didn't you pick the one on the top? Or why didn't you pick the one on the right? It does not matter. You can pick any 3 of them, and you can do it just like this. You just have to pick one of them. And I'm going to be honest with you guys, I worked this problem out before I did this video, and I actually worked it out wrong. I miscounted in my head, and I did not mean to show you one like this. However, I've already got too far into it, so now I must account for it. So here's the deal. It can look like any of these 3. And let me just go ahead and tell you there's a vocabulary term I have not talked about, I have not mentioned, because it's something that's above your knowledge base right now. And this is like if you were to look this up on a vocabulary crossword puzzle, this is what it would be. Any chemical structure that can be drawn different ways but represent the exact same molecule has this. And this is the word. It's called resonance. And I always misspell this word. Resonance. Okay, I will not test you on this at all. But one more time, let me tell you what it says. Any chemical structure, and again, this is nitrate we're drawing, that can be drawn more than one way. How many ways do you see? 3. That all accurately represent the same molecule, then it's called resonance. That's what it's called. Again, you will not be tested on this. I did not even mean to show you this, but I was too far in to back out. So let me show you a polyatomic that actually works without resonance, because there are a lot of the polyatomics do have resonance. So let me show you one that does not. So it's on the very back, number 20. Let's look at sulfate. So number 20 is sulfate. So S, O, I have one S, I have 4 O's, I have 6, I have 6, that needs to be times, so 6, and then 24 is 30, but can you stop there? No, please, please, please do not account for this. And you know what, I actually made a mistake on that last one. I did not even think about it, and I need to make a point of emphasis on this one, because I completely botched it. So let's go ahead and subtract those two. So 32. The whole resonance thing threw me off, is why I did not figure that one out. Alright, so S, I'm going to go ahead and connect all my 4 O's, all my 4 O's. So that's 2, 4, 6, 8. So 32 minus 8 gives me 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Alright, so good news is this one leaves me with 0. And everybody has its happy octet. Every oxygen has its octet, and sulfur has its octet. So this is the one you need to pay attention to. Anytime you draw a polyatomic, there's two things you have to account for. First of all, you have to account for the 2 electrons being added in, and then this is the biggie. If you do not draw it this way, and I made a big point of emphasis, I will count off. If you do not put this structure in brackets and show the charge, it is incorrect. I don't care what the structure inside of it looks like. I don't care if it's perfect. It's incorrect if you don't put the brackets and put the charge. So you may want to put a big star beside this one and put brackets and charge. And so the way I think about this is anytime I ever have a polyatomic, and again, now you can go back and look at the nitrate and figure out why I messed that one up. Forgot, because like I said, the resonance threw me off and I forgot to do it. Brackets and charge must always be brackets and charge must always be a part of a polyatomic. So let's look at 21. This is how I would always recommend doing it. This is sulfite, boom, polyatomic. Automatically draw me some brackets, plop that sucker up there, and fit that structure right inside of it. Okay, doesn't matter what it is, get your brackets and do it. Look at 22. ClO3, that's chlorate. I don't care what that structure is going to look like. Draw me some brackets, put a charge out there behind it. Okay. So please, please, please do not mess that up. You're going to have to draw a polyatomic on the test. It will not be one with resonance. I'm telling you that now. So again, just please make sure that you can understand all of these. So hopefully you have gotten enough knowledge from this that it will help you out in the long run. If there's anything else you need, please do not hesitate to ask. I'll be glad to answer any of those questions. I'm actually going to finish working on the key, and I'm going to scan the key, and I'm going to email the key out so you actually have the answers in front of you. All right, so hopefully this has been a well-learned video.